Introduction to the new tyFlow value operator workflow. Looking at this value operator workflow that's new in tyFlow, that pretty well changes everything, right? So what do I mean by this arrow back and forth here? Well, it means that in a way information gets transferred from the source operator to the value operator and more or less back again, right? And one example of that would be whatever our starting value gets transferred over to here and gets adjusted depending on what we have set here. And this is kind of where it starts. So initially, what kind of starting value do we want to start with? Then what kind of adjustment do we want to do? Are we adding to a value? Are we dividing, inheriting, multiplying, subtracting, etc.? And then how is that adjustment calculated, right? So is it calculated by a frame, by a script expression, a property, surface, texture map, value, or when we do percent, it's more or less the graphs. Then do we want to vary our result, right? And then what value do we want to vary that by? And then we can do some adjustments, right? Like we can, if we have a negative value, right, can we turn it back into a positive value? We can normalize the values, which I'll explain, and we can clamp the values, and then we can multiply. And then, once all this has been done, then in a way, this goes back into our flow as a final adjusted value. So, that's kind of a fairly decent representation of what's going on here with this value operator. And it really adds a lot of power. And let's have a look at some of this in more detail. Okay, so this is going to be my only advertisement in this tutorial, and I feel a bit embarrassed about doing it. But on Udemy, I have a good course that is this style of training method, and it tries to show you parameters, settings, understand concepts, and it's called tyFlow, the Missing Manual. It's by me, Robert Anderson, but I'm also known as Fireflight Photo, depending on my YouTube or Udemy channel. And right now it's at 23 hours. It's good content, and I'm adding a whole new section on the value operator, and it's going to keep growing. It's an ever-growing training, and it's only $35, of which I only get half. That's my advertisement. If you want to support me in making more videos, that's how you can do it. Thank you. So taking a look at the value operator workflow, we'll take a look at this quick example where we're birthing 20 particles over 10 frames. We're positioning them on a selected surface, which is this face facing us. We're giving them a 3D sphere shape, which is scaled at 100%, so no scaling. And we're going to use the scale operator to show the workflow for the value operator. And at the moment, this is default and everything's set to 100%. I have a script operator in here so we can print out the Z scaling and see what happens when we do this value operator. So here we are, we want to affect the Z scale, and we want to use a value operator to do it. So we click this little diamond, which gives us access to the value operator, which then we can see now this value operator expanded the scale Z underneath our scale operator. We click here and drag out to a new event, and that is a value event, which can only really hold value operators. And the current default is P block is the type, and it's set to absolute value of 100%. So what really happened here at this point is we've done nothing, because what we've done is we've had a particle that's scaled at 100% being set to 100% scaling. So the net result is we open our scripting listener and we cleared this, clear all, and we refresh here, we can see that all 20 particles remain at 100%. So we can by default, this P block is the default, which means it's going to drag over the original value, and then you can play around with it here and make calculations, adjustments, etc. The other choice is 0, in which case it's supposed to zero the value, but I find it doesn't quite work. I have to go in and zero it in the absolute. And then from source spinner, which means that it will constantly get the value from the source spinner, and in this case the source spinner is this value percent back here. You can see right now in P block mode we can't access it, but if you have it from the source spinner, this becomes active, and then you can either keyframe and animate that and it'll still pick up the value from here. So having said that, now we're getting this 100% set of our particles. Well, we're going to do something more to it. We can do what we call build a stack, which means having more than one value operator here. So if we hit the tab key and start to type value and add a new value operator, and the way this works is from top to bottom, left to right kind of thing. So originally we set the default, which was 100%, which did nothing to our particles, but now we want to do something. So then we come over here and we have some choices: add, divide, inherit, multiply, set, subtract. For this one we will use add, and we're going to add an absolute value, and it's going to be 1, which is equivalent to 100%. Technically our particles should now be showing at 200% scale in the Z direction, but they're not. And the reason they're not is A, that it matters what order these value operators are in, and B, it matters where the value operator is connected. And right now we're connected to the first one. We really need to get connected to the second one to see the composite result. So if we look over here, we can assume that this is 200%, but if we really want to know, we can go back into our scripting listener, clear all, and because I'm looking at the Z scaling, I can refresh and we can see the value for all 20 particles is now 2.000, which is the equivalent of 200%. Variation percentage, what exactly does it affect? I have a full explanation of this on my Udemy, but in this quick intro tutorial, so basically we've birthed some particles, we've placed them on the surface, we've given them the shape operator, and it's at 100%. And now when we look at our stack here, we're setting it to 1, which is keeping the 100%, and then we're saying add 1 with up to 100% variation. Now, a lot of us, including me at times, have thought this is a plus or minus value, but I've done some testing, and what I can tell you is that variation percentage here is very the number that's in the box above, from anywhere from 0 to 100 and not above. So in that sense, it's not a plus minus value. So if we look at that example here, we are adding anywhere from 0 to 1 to our original 1 scaling. And when we looked at this, the script printout here of our Z range, we can see that we get one value very close to 2, which is 1.994, and we get one value that's very, very close to 1, which for the life of me I can't see right now. There it is, 1.063. So we can see that if we introduce 100% variation, it's just a value between 0 and 1, and it's not actually plus minus, so just keep that in mind, and that's what the variation is going to do for us. Alright, so this P block default thing is only relevant or active for the first in the stack, right? So for this second one, it's not active, it's being ignored. What is active throughout is what type of operation. So in this instance here, we're telling from our last example to add 1, right? Well, we can also use these other methods. We can set it, or we can divide it, inherit, multiply. Let's just do one other here, and let's say we divide. Well, right now our starting value is 100% or 1, and we're dividing by 1, so we essentially get the same result. 1 divided by 1 equals 1, and 100% divided by 1 equals 100%. So if, for example, in this divide example, I change this to be 2, right? So now we're halving it because we're dividing 100% by 2 and we're getting a 50% result on all of them. I'm not using the variation percentage because we want to understand what's going on. And if I divide by 4, we're going to get the equivalent of 25% reduction in the Z height, right? Now, if I go half, like 0.5, I'm actually going to double them, right? Because 100 divided by 0.5 is 200, correct? So there we go as far as using this operation mode in a quick introductory type manner. So far, all the examples we've been using this value, an absolute value, and it's basically been whatever this value is here plus the variation that we might have applied, and for right now we're keeping this variation at 0. So we can also come in here and click a range, in which case we can type a minimum value and a maximum value, right? So if we come in here and we're doing divide, so let's maybe switch something to multiply, right? And let's control the values a bit more. So let's say we want to multiply anywhere from 1, which is no change in scale, up to say 5 times in scale. So now we're getting a random scaling based on this value operator stack on our particles in the Z direction. This curve here is always in play. It's just a matter of which curve are you using to affect this minimum and maximum. I have a great in-depth explanation on this on my Udemy, and my Udemy is going to have a lot more content coming very shortly. But the general idea is a linear graph like this is basically going to result in an average amount of change, where the values go from the minimum 1 to where the values go up to 5, and it's really just an average of the range. If we still have our script available here and we clear this and we refresh, you can kind of see the kind of range you're getting, right? And so there's some presets here that you can use, and you can even manually tweak this curve. So that's kind of value, but value isn't the only choice. We also can have the current frame affected. We can do a C+ expression. We can base it on a property, and then the property would be something like this. Choices, right? And when you look over here in the left hand side of the cube, we got all these black spheres. That's because the surfaces are invalid because we are multiplying by a negative number. All the positive numbers of position X are on the right of the middle of this box, and negative. Now we could go in here and click absolute, which will turn any negative values into a positive and thus eliminate those invalid polys that we had created. So we can see there's going to be a lot of choices and a lot of options for affecting how these value operators might change the result based on all of these different settings: surface, texture map, value percent, etc. We've already talked a bit about this variation percentage, and I'm not going to touch this relative to property. And let's have a look at this whole section at the bottom here quickly in this quick starter tutorial. Alright, this normalization thing, normalized value, that's in this surface mode, right? What exactly does this mean? Well, normally normalization means trying to generate values between 0 and 1 and kind of standardize a set of values. In this case, because it's based on a minimum and maximum you can set, I would more or less say that it's normalization but adjusted based on what you set the range to be, and I'll explain this in a second, but you can think of it as the max value here would be a division. So if I'm normalizing 0 to 100, any values that were there before normalization, in this instance would be like divisible by 100, right? And that would be the new value. So let's just take a look at some examples I set here. So with this current setup and the velocity magnitude being affected, with no normalization, these are the values you get. You can see that if I set the range 0 to 100 and I just use MaxScript to derive all these values, so we can also see the benefit of a little bit of scripting knowledge. But you can see that if we set the range 0 to 100, these are the new values that are generated for the velocity. And as such, the particle boxes are much closer to their original sources. But if you also look mathematically, now I've rounded it down to 3 decimal places, but we can see that mathematically it's basically the numbers on the left, the original unadjusted ones, divided by 100, right? And at 50, 0 to 50, we're more or less halving the unadjusted numbers, and at 10 it's almost like 10%. So maybe that gives you more of a visual perspective of what normalization does in this regard. And just to see the results visually here, this is at 100, right? This is at 50, and this is at 10, right? So we can kind of see what's going on. But this will give you a good idea of what normalization is actually doing. And inverting it is going to make, it's not a perfect invertation of the numbers we see here, but essentially you can think of inverting this normalization as inverting the curve. So if I click that, we can see the curve, the particles actually went down. It's not an exact invertation of the original kind of curve. The main point being is that if you invert the values, instead of the particles that are furthest away from the sphere getting the most velocity change, it's now the particles closer to the sphere that are getting the most velocity change. And in Tyson's example where he had some paper box-like things on the surface of a icon, sphere came down and all the particles launched into the air, and the ones closest to the sphere went the furthest. This is that will be an example of using invert to create that effect. Let's take a look at this clamp value and multiplier and see if we can figure out exactly what that does. So what does this clamp value thing do? So we've turned normalization off, so the current data set is whatever tyFlow calculated to do with the magnitude, velocity magnitude based on the distance to the sphere, and we got the printout of the values as well here in the MaxScript listener, and they match this row. So this is the unadjusted data set that was generated by tyFlow. If we clamp values, and by default it comes up with 0 to 1 as the range, we can see here in this table that only particles 11 and 12 had a velocity of less than 1, so we can see that all the other particles had their velocity magnitude clamped at 1, and we can also see that visually in the viewport. And it doesn't have to be 0 to 1, like we could go say 0 to 5 for example, right? And then we see an update in the MaxScript viewport here, and you can see that you have a range of particles in the middle here that were below 5, so their values didn't get clamped, and the ones that were above did get clamped. So that kind of gives us a good idea of clamping. Now it doesn't have to start at 0. If you want, you can start higher. For example, if you want to clamp from 1 to 5, we can see that we got some clamping on the top end of the range, we got some clamping at the bottom end of the range, and so now we have 2 batches of numbers that still fit in that, range, and they're allowed to exist, and you can see the pattern that's generated. So basically that's what we're doing when we're clamping the value. And same as in the normalizer here, we can invert that. So if we invert that, you can see you get this kind of inverted pattern based on that clamping. And I hope that helps explain what clamping the values do. So let's look at the multiplier and what it does. The multiplier, what does it do? We'll leave this clamping effect and inverted result in effect for this example. So you can basically think of 100% being 1 to 1. So whatever the current value is, it stays that value if you've got 100% here. If you put 200 now, right, and we can see up here in the max script listener that one of the values is 1.4 for magnitude. We're now going to type 200, and you can see it's now 2.8, so we effectively doubled the magnitude. So basically this multiplier happens after everything else that's happened here, and it multiplies the end result, right? And 500 would give you even more magnitude, right? And we can see that in the viewport, and we can see it here. And obviously we can also go lower. So 50%, we would actually halve the magnitude, right? So that was just a quick and dirty introduction to the value operator and the new workflow. And I'll leave you with this example that Tyson provided, and it's pretty cool. Have a good one, everybody. See you in the next one.